Hello and welcome. Today we are continuing our reactions of alkyl halides, and what we're going to talk about next are elimination reactions. So I have an outline here of how I'll be presenting the material for this part of chapter 7 in the Klein textbook. And today we're going to be reviewing what alkenes look like and talk about their stability. And we'll also get into our first elimination mechanism, which is the E2 elimination. So let's just review what an alkene looks like. The alkene is the class of compounds that contains a carbon-carbon double bond. And I have a model here of what a carbon-carbon double bond looks like here. And what we're showing with the blue and green lobes here are the one p orbital. And over here we have a second p orbital. And that's how we form a pi bond. So when we want to think about the reactivity and the structure of an alkene, we always have to remember that we have a pi bond. That's what we, for a double bond, we have a pi bond and we have a sigma bond. So the plastic bond here in the middle represents the sigma electrons that are between the two nuclei, and the pi electrons are above and below the plane. Okay, and the hybridization and the geometry of this of each carbon in the double bond, in any carbon-carbon double bond, is sp2 hybridized, which means those hybrid orbitals are arranged in a trigonal planar arrangement. Trigonal planar. So when we go to sketch a carbon-carbon double bond, we could put all the sigma bonds in the plane at bond angles of 120 degrees. Okay, and so that's, I don't know if you can see the black bonds here are all 120 degrees, all in the plane. And then we have this p orbital that's now coming out and going back. And so we can kind of sketch that as a lobe that's coming out and a lobe that's going back. And we can draw two parallel p orbitals on each carbon, and then just kind of connecting the top and bottom is how we could represent a pi bond. Okay, or we could maybe draw the alkene, the carbon-carbon double bond, where we could see the p orbitals very clearly. But when we do that, now all of a sudden this bond is coming out towards you and this bond is pointing away. So now we have two of the sigma bonds are going to be wedges and two are going to be dashes. We'll tip it just a little bit so that we could see both the wedge and the dash bonds. So that's another way that we can sketch it, is we can draw the p orbitals very nicely, connect the top and the bottom, but now our sigma bonds are going to be, two of them are going to be sticking out towards us and two are going to be pointing back. So the key here is that the p orbitals are orthogonal to the sp2 plane, meaning at a right angle, So those are two ways that we could sketch this. And we could also think about how to describe that double bond. We have one sigma bond and one pi bond. The sigma bond is made by overlapping the sp2 hybrid orbitals on each carbon. And the pi bond is from p orbitals, one p orbital on each carbon that is overlapping to make the pi bond. So just a little review of how we can sketch p orbitals and what they look like to make pi bonds. And that's what an alkene would look like. So a couple of things we want to note about pi bonds. They are higher in energy than sigma bonds. That makes them more reactive, easier to break. And another thing that's interesting about them is that they are electron rich. So if they are electron rich, what kind of reactivity can we have? They can act as a nucleophile, or it can act as a base. We're going to see all that in the very next chapter, in chapter 8. We're going to see lots and lots of reactions of alkenes, of carbon-carbon double bonds. Okay, so what are we doing right now in chapter 7? We're going to be learning how to synthesize those that functional group and how to make pi bonds. The way we're going to make a carbon-carbon double bond is by doing an elimination reaction. Okay, before we get to those mechanisms though, let's talk a little bit about alkene stability. Not all double bonds are equally stable. So what are some things we could do to stabilize a double bond? One thing is if we have more than one double bond, then we can put them in conjugation with each other. And so that means we have alternating pi bonds. In other words, if we go, if we take a look at these two alkenes, they're called dienes, and we have two double bonds. We could see that if we think about the p orbitals that make up those pi bonds, in this case, there's no relationship. In this first structure, there's no relationship between those two pi bonds and those four p orbitals. But in the second one, when we draw on the p orbitals, hopefully you could see that there is going to be some interaction between the adjacent p orbitals. In other words, they're going to have some resonance delocalization of those pi electrons. And that is a good thing. So this is the example that is conjugated, and that makes it more stable, The relationship that we have to be conjugated is when we have a double bond, and then a single bond, and then a double bond, and so on. Just one single bond, one sigma bond in between the two double bonds. Okay, in the second case, we have an sp3 hybridized carbon that's in the middle here, right? There's two hydrogens. And so that stops the communication from happening between, this first pi bond and the second pi bond. They are not interacting. So interactions of pi bonds is a good thing. We call that conjugation. We're going to see lots more of that down the road when we look at things like benzene rings and aromatic compounds. But just wanted to put that thought in your head. If we ever come across an example where we have multiple pi bonds, our goal is going to be to get them to be conjugated. If that's an option, that would be great. Okay, so what else can we do to stabilize an alkene? It turns out that the more carbon groups, the more alkyl substituents, that's how we would describe carbon groups. The more alkyl substituents that we have on a double bond, the better. And let me get my pen back. There it is. So how many carbon groups can you fit on a double bond? Well, every double bond has 4 positions that can be filled. So if all 4 of those positions are filled with carbon groups, we use the letter R to represent just a random carbon group, methyl, ethyl, propyl, something like that. We describe such an alkene as tetra substituted, and that is one of the most stable alkenes that we can have. Alkenes love having carbon groups attached. Okay, that would be more stable. Than this next one, which we would describe as tri-substituted, because it has just 1, 2, 3 carbon groups attached to the alkene, right? This 4th position has just a hydrogen here. We could draw that in if you want, just for comparison to make sure we see what that 4th position is. Okay, and a tri-substituted alkene would be more stable than any of these next 3 examples, which are all examples of di-substituted alkenes. So each of these has just 2 carbon groups, and it actually, there's 3 different ways that you can arrange 2 carbon groups on an alkene. If they're 1, 2 to each other, if they're on opposite carbons, we could arrange them as either the trans or cis arrangement. Trans or cis. So when the 2 groups are on opposite sides of the double bond, we call that trans. When they're on the same side of the double bond, we call that cis. And when they're on the same carbon, we describe that as being geminal. The geminal relationship, or just gem for short. Okay, and of these 3 arrangements, the only one that you should know about its stability is that the best one of all 3 of these is the trans. The trans is more stable than either the cis or the geminal. You don't have to worry about trying to distinguish between those 2. Okay, so what makes the cis less stable than the trans? What makes it less stable? Because these 2 carbon groups are going to have some interactions. They're going, because they're right next to each other, they're eclipsing each other. This will have some steric hindrance. So the sterics involved in a cis relationship makes it less stable than trans. All right, and then finally, all of these are better than this last one, which we would just describe as a monosubstituted alkene. Okay, or we could also describe it as a terminal alkene because it's at the end of a carbon chain. It's the very end of a carbon chain, the terminus of a carbon chain. So a terminal alkene or a monosubstitute alkene is the least stable. So we're gonna, as we're doing these elimination reactions, in many cases, we're gonna have choices on where to place the double bond in the product. And we'll see that if our goal is to form the more stable alkene, that always correlates to the more substituted alkene. Very good. Okay. Now, finally, let's talk about that stereochemistry, the spatial arrangement of the groups around it. What we just highlighted here is that the trans is more stable than the cis, which is true. Again, we have that steric hindrance here between the cis groups. Okay, now when is there an exception for that? So cis is less stable because of sterics. Let's put steric hindrance, make sure we see a couple different ways to describe that. Nope, sorry, we're missing an E there. Hindrance. We call it steric hindrance when groups, bulky groups kind of crash into each other and trying to occupy the same space. So this is the cis arrangement, has some interaction between those two methyl groups, and here the trans relationship, they do not. Okay, so when's the exception? The exception is when they're in rings. When you have a double bond in a ring, actually it's the cis that becomes more stable. In fact, in small rings, only the cis is possible, because if these two carbon groups are going to be attached by a ring, they have to be arranged on the same side of the double bond. They have to be cis to each other. So most double bonds in rings are cis. It's possible to have a trans double bond in a ring when you get to be more than 7 carbons. So this is an 8 carbon ring. We call that cyclooctane. And when you put a double bond in it, we call it cyclooctene. So that E tells you that there's a double bond somewhere. And this is the cis arrangement because the two carbon groups are on the same side of the double bond. And this is the trans relationship because the two carbons are on the opposite sides of the double bond. Okay, and so this is the case now. Typically trans is more stable, but when it's in the ring, it becomes less stable. Cis is going to be more stable. So what's the problem here? Well, again, it's large enough that these two carbons are able to reach each other, but the problem is when you draw on the hydrogen atoms, you see that that hydrogen atom now is kind of forced inside the ring. So now we get some of that steric crowding again and some other strain. So in general, when we're drawing rings, we typically kind of stick to drawing these polygons like this, and then we just insert the double bond at any position, and then that's going to automatically make it the cis stereochemistry. Okay, so those are some things we want to know about alkene stability. There's one other one. This is just an FYI. This is not going to come up very often, but if we happen to have systems that have multiple rings, bicyclic systems, something like that, what we want to do is try and avoid putting a double bond at the positions known as bridgehead carbons. Bridgehead carbons are the carbons where we have, let me see, that probably doesn't show up so well. Let's go back to a pen. The carbons that are shared by multiple rings, when all those carbon groups, carbon bridges come together. So if you look at this compound, you could describe it as these two carbons are connected by 3 bridges, right? Here's one bridge, and here's another bridge, and here's another bridge. And so these are described as the bridgehead positions. And the rule here, it's called Brett's rule, says that we don't want a double bond at the bridgehead position. So this second structure would be unstable, would be very unstable. And that's because the double bond is touching one of those bridgehead positions. It has a very hard time being planar at that position, and it's not good. But this one is okay. You can put a double bond in another position as long as it's just not to one of these carbons. Okay, so that's known as Brett's rule. Again, very rarely is this even going to come up, but just down the line, if you ever happen to see something like this, we'll know that we want to avoid a situation like that second one. Okay, so let's see an example. Let's see an example. If you want to pause the video and see if you can predict of these three alkenes, which one is the most stable and which is the least stable. That would be a great exercise. And I'll go through it together. So remember, every alkene rather has 4 groups attached to it. And so here's my carbon-carbon double bond. I have 2 positions. In this first one, I have 2 positions that are carbon atoms. And that's it. The other 2 positions are just hydrogens. So sometimes it helps to draw on the hydrogens while you're getting the hang of this to see how many hydrogens. There's 2 hydrogens and 2 carbons. So we describe this one as a di-substituted alkene. This first one is a di-substituted alkene. It has 2 carbon groups. Okay, how about the next one? All 4 positions attached to the carbon-carbon double bond, right? So we're just inspecting the carbon-carbon double bond, and we're saying, okay, what is attached to the carbon-carbon double bond? In this next one, all 4 positions are occupied by carbon atoms, alkyl substituents. So we would describe this as a tetra-substituted alkene. And how about this last one? Do you see that it has only 1 hydrogen atom attached? So that means all the other 3 positions, are carbon atoms. We describe this as a tri-substituted alkene. So they all have different substitution patterns. So which is the most stable? The one with the greater number of carbon groups would be the most stable. And so the tetra-substituted would be the most stable, and the opposite, when you have the least number of carbon groups, that would be the least stable. So that would be the di-substituted down here on the first structure. Least stable, and most stable. Okay, very good. So identifying any alkene as being monosubstituted, di-substituted, tri-substituted, or tetra-substituted, and then also we can be able to classify them, and then we could also rank them in terms of their stability.